All right, our next lesson, we're going to learn about buffers and buffer solutions. So we'll start off with this calculation. This is not in your notes. If I go ahead and move to the next slide, this one is in your notes, but I want to do a comparison first. So if you have some room maybe on the back page of your note packet or some other place, go ahead and do this calculation. Determine the pH of a solution that is 2.5 molar in ammonia. The Kb for ammonia, I'll just flip ahead again to this next question. Kb for ammonia is 1.8 times 10 to the negative fifth. So we're not working on this question here, but rather this one here. Go ahead and pause and set that up. All right, so here's our setup. Set up an ice table, write our Kb expression, solve for X. X is the concentration of hydroxide. So if we negative log that, we're going to get the POH. So I kind of combined that into two steps. So 14 minus the negative log of the OH minus concentration. So minus and minus becomes a plus. So that's why this is plus here. You can do minus and minus if you want. And we end up with 11.827. I'm good with 11.83 if you want. So either the correct number of significant figures, or we can do two decimal places. That's fine as well. All right, now looking at the example in the notes, it says calculate the pH of a solution that is 2.5 molar in ammonia and 2.5 molar for ammonium chloride. All right, so this is a buffer solution. So what exactly is a buffer solution? Buffer solution is a solution that contains a weak base along with its conjugate acid. So they're both present in solution at the same time. So the conjugate acid of ammonia is ammonium, and you have both of those substances present in somewhat large quantities. Or that's for a basic buffer. An acidic buffer contains a weak acid along with its conjugate base in solution. So we have to have both. And so it's got to be a weak acid or a weak base. We have to have a solution that contains both an acid and its conjugate base, or a base and its conjugate acid. The reason is that a buffer solution is a solution that resists changes in pH. So if you were to add, say, hydrochloric acid to a buffer solution, what would happen to the pH? Well, the pH would go down because you're adding an acid, but it wouldn't go down by that much. Likewise, if you added a base to a buffer solution, the pH would go up by just a little bit. And so we need to recognize that we have a buffer solution. So you need to recognize that ammonia is a weak base. You need to recognize that ammonium is the conjugate acid of ammonia. So let's set up a couple different equations to show you what's going on here. First, I'm going to start off with a balanced dissociation equation for ammonium chloride. So ammonium chloride is soluble in water. And so a solution of ammonium chloride contains ammonium and chloride. And we don't really care about the chloride ions, it's the ammonium in solution that we care about. Not only do we care about the ammonium that's in that solution, we care about its concentration. So it says we have a 2.5 molar solution of ammonium chloride. And what's important to know there then is because of the 1-to-1 ratio of ammonium to ammonium chloride, the concentration of ammonium is also 2.5 molar. The other equation I want to write is the ionization equation for ammonia, just like we saw on the last example. So let's go ahead and write that. So notice our balanced dissociation equation, we have a one-way arrow. This substance completely dissociates. It's a soluble salt, and so it completely dissociates, whereas our weak base only partially ionizes. So setup looks the same. So we have our ionization equation, we have our Kb expression. Again, we're looking for the same thing as last time. We're looking for pH, and so before we can find the pH, we need to determine the OH minus concentration, and then from there we can determine pH. So let's, like before, set up our ice table. We've got 2.5 molar for ammonia, and the big difference here in our setup, very, very, very important. We talked about this with solubility last unit's common ion effect. So this is very similar to the common ion effect. We have ammonia a solution of ammonia that is present with one of its ions. So we have ammonium already present in solution, not from this process, but from this process here, the dissociation of the ammonium chloride. So be careful. Both of the initial concentrations are not zero. You will have an initial concentration of one of these two ions. The rest is the same from there, with one little difference that I'll show you in 1 second. All right, so we have our equilibrium. Whoops, that is not X there. That is 2.5 plus X. We have our equilibrium concentrations. Let's plug them into our Kb expression. I'm going to go to a new slide just so I have some more room to work here. So we have 2.5 plus X times X over 2.5 minus X is equal to our Kb. And again, let's talk about this. Kb is small, 10 to the negative fifth. So what that means is only a small amount of the base ionizes. And so what that means is that X is small. So once again, we're going to assume X is small. And again, what we're talking about is not only this X this time, but this X as well. If X is a small number, then 2.5 minus X is really just 2.5. And if X is a small number, then 2.5 plus X is really just 2.5. So we have 2.5x over 2.5 is equal to our Kb. You don't have to always have the same concentration of the base and its conjugate acid or acid and its conjugate base. Just so happens that they are the same concentrations here. So those cancel. We end up with x being 1.8 times 10 to the negative fifth. Now, something I want to talk about is going back to Le Chatelier's principle. So if we increase the concentration of ammonium, so we're adding, let's say we take a solution of ammonia, and to that solution we add solid ammonium chloride. That ammonium chloride is going to dissolve, it's going to dissociate, we're going to have some ammonium ions in that solution. What is the increase in the concentration of ammonium going to do to this equilibrium? Well, if we increase concentration of NH4 plus, it's going to push the equilibrium to the left. If the equilibrium goes left, what happens to the amount of the NH3 that ionizes? The amount of NH3 that ionizes is going to decrease. So the presence of that common ion, like we saw with solubility, suppresses the ammonia from ionizing, so less of it ionizes. And so again, because of that, that makes X an even smaller number. And so really, we should be confident in making that assumption of X being small. I didn't do it on the last one, but make sure you always check your assumption. So we can do both 2.5 minus X and 2.5 plus X. And we're going to get the same thing. We're going to get 2.5. So our assumption is valid. All right, let's go ahead and finish this problem. So the question asked originally for the pH of this solution. Be thinking about what the pH of this solution is compared to the one in the previous example where we had just the ammonia and no ammonium in that solution. Go ahead and pause and do that now. All right, should end up with a pH of 9.255 or 9.26. I'll be good with that as well. Look at that. pH of this solution is significantly lower than the pH of the 2.5 molar ammonia solution we saw in the last example. So again, let's talk more about why that's the case. If you increase the concentration of NH4 plus, that pushes the equilibrium to the left. What happens to the concentration of hydroxide when this happens? Well, concentration of hydroxide decreases. And when the concentration of hydroxide decreases, what effect does that have on the pH? Well, the pH will also go down. The solution, if OH minus is going down, then H plus is going up. and therefore pH is going down. Make sure this all makes sense. Make sure you understand why the pH of this buffer solution is less than the pH of just the weak base solution by itself. All right, if we skip ahead in the notes, we'll find another example of a buffer solution. So let's do that. So this problem is past the acid helper, the very last example, number 3 in that section. And then again, I want to do another comparison. So either divide this space up in half, or better yet, do what I ask of you first on the back page or a separate sheet of paper. Like we did last time, let's just do this. Find the pH of this by itself. So let's say you have just a 1.5 molar solution of nitrous acid. Ka is 4.5 times 10 to the negative fourth. Find the pH of that solution by itself, and then we'll go over that, and then I'll have you do this buffer calculation. Pause and find the pH of the nitrous acid by itself first. All right, so if we just look at the nitrous acid by itself, we should get a pH of 1.585. So your setup is x squared over 1.50 minus x equals our Ka. Assume x is small, so x squared over 1.5 equals 4.5 times 10 to the negative fourth. Solve for x, negative log that, and you should get this value. All right, now let's think about this. We have a solution now here for this problem, 1.5 molar for nitrous acid and 1.5 molar for sodium nitrite. Nitrite is NO2 minus. What is, and again, be thinking about the last problem we worked on, what exactly is NO2 minus to HNO2? Think about that. Pause if you have to. NO2 minus is the conjugate, what is it if it has one less H plus? NO2 minus is the conjugate base of HNO2. So once again, we have a buffer solution. This time a weak acid along with its conjugate base, both in relatively large quantities. Like I said, it doesn't have to be the same concentration, though it is the same here once again. And so this is a buffer solution. So the presence of the nitrite ion is going to suppress the nitrous acid from ionizing. Less of it will ionize. Think about what effect that has on the H plus concentration of the solution. And as a result, the pH of this solution compared to just the nitrous acid by itself. Go ahead and pause the video, set this up, and see what you get, and see if your prediction agrees, or your answer agrees with your prediction. All right, so here's our setup. So same as before, we start off with a balanced dissociation equation for our salt, sodium nitrite. And so again, the key thing here is we're trying to determine the concentration of the nitrite ions in solution. And once again, we have a 1-to-1 ratio of nitrite to sodium nitrite, so 1.5 molar for nitrite. That is initial concentration. So set up our ice table. We have an initial concentration for the nitrous acid, initial concentration for nitrite, 0 for H plus ions initially. We get our equilibrium concentrations. We're going to take those and plug them into our Ka expression, which looks like this. We have to make this statement. We have to state that we're assuming x is small, so we can simplify the setup. So if x is small, then 1.5 plus x is about 1.5, and 1.5 minus x is about 1.5. Once again, those cancel. They don't. It's not always going to be that way. And so we get x is equal to 4.5 times 10 to the negative fourth. If we go back to our ice table, x is our concentration of H plus. So make sure you know what you're solving for here. And so negative log that will give us the pH. I believe I gave you the wrong significant figures on the previous examples. I forgot to take into consideration our KB on the last example had 2 significant figures. So your concentration that you calculate for OH minus will have 2 significant figures, and your pH value would have 2 decimal places not 3 decimal places. So I apologize for that. So this should be the right answer, pH of 3.35. What do you notice? So if we go back and compare to the pH of the nitrous acid by itself, that was significantly lower, I erase it now, 1.5 something. And then this buffer solution has a pH that is significantly higher. Why is that? Well, once again, it has to do with the common ion effect. So the presence of nitrites is going to do what to this equilibrium? Push it left or right? Well, equilibrium is going to shift to the left this way. And if the equilibrium shifts to the left, what's going to happen to our concentration of H+? Well, concentration of H+ is going to go down. And if the concentration of H+ goes down, what happens to pH? pH goes up. So we end up with a solution that has a pH of 3.35. We'll get into much more detail with buffer solutions if you take AP chemistry or IB chemistry. So this is a good brief introduction, and we'll do some more examples in class. First step is recognizing that you have a buffer solution. In this case, we have weak acid, nitrous acid, along with its conjugate base being nitrite, both present in large quantities. That's an acidic buffer. First example is called a basic buffer. We have a solution of a weak base along with its conjugate acid. That concludes this lesson. Next time we will discuss titration curves. Thanks for watching.